Hello, this is Rob Smith with Johnson Controls and SprinkCAD. This is a recorded presentation of Autodesk University 2019 Design and Calculation of Fire Sprinkler Systems in Revit per NFPA and other standards. And the fact is that we're really going to be focusing on NFPA here, talking about performing hydraulic calculations on a Revit system, a Revit model, using the SprinkCalc software directly from within that Revit model. Then we're going to look at some other tools. And if you're watching this demonstration, then you've logged in and are accessing recorded classes from Autodesk University 2019. And would like to make it clear at the very start of this presentation that all of the tools that are about to be shown are licensed tools through the SprinkCAD for Revit program. That is a commercial software which requires a license, and there is a cost for that license. There are no free versions of the license. You need to contact someone from the SprinkCAD group in your area or speak to a Johnson Controls representative in your area to get information about how you may access these tools. And remember that this recording, made in November of 2019, demonstrates the status of these tools at that point in time. We are constantly making adjustments and improvements to these tools. We've only just begun on the journey of creating tools for the fire protection engineer, designer, and contractor in the Revit environment. We're going to start with this elementary school. This is a project that has been distributed with the Revit software at various versions in the past, perhaps 2017. School may look familiar to some, and I'm going to take a moment right here to say, well, we have an elementary school. We're going to run some calculations, and we're going to do so in Revit. I'm going to do a sidetrack with a piece of software called SprinkCode Connect. I bring this up because SprinkCode Connect can help the fire protection designer, engineer to determine the density and the coverage necessary in a given project. So I'm going to come back to SprinkCode Connect, but I'll point out up here across the top, this is reached at SprinkCode.com. And I'm going to zoom in. When you reach SprinkCode.com, it's going to ask for a user login. Of course, you have the forgot username, forgot password, and by requesting access, you'll get a screen come up asking you about your business type. You may be an architect, you may be in building construction or inspection, a sprinkler contractor, an engineer, drafting person. There's an opportunity for other plumbing, remodeling, repair, and maintenance. And then the business name, address, city, state, zip code, what country you're in, a business email, and a phone. And if you do not have a SprinkCAD license, that's okay, because this software is free if you are referred in, and all you have to do is fill out everything that I just mentioned and then put in my name, Rob Smith, as the person that referred you to the software. Then in setting yourself up for a business access like this, we limit the access to one administrator per company. So the person who initially signs up becomes the administrator. So we ask that if someone in your company wants to give access to a few individuals within your group to this SprinkCode software, have that person who is going to act as the administrator fill in this information, specifically the business email address, and then that person's username, first name, last name. So this is, of course, is one of those, this is my username, address, city, state, etc. here, that person's email address and a phone number for contact, and then you create your own password, and of course you have to enter it twice, and then you have to accept the end user license agreement and hit register. So don't forget, you've been referred by Rob Smith. That's going to get you access into the SprinkCAD software. So I'm going to minimize this, take a look at this particular drawing in Revit, and talk about it just a bit. So switching over to a different view, I'm going to say right up front that I am something of a novice when it comes to Revit. And you're going to pick up on that fact real quick as we go. Double-clicking on this section so that I can have a look at this particular section view. And I went here, you'll see why in a moment, because this portion of the building I'm zooming in on, I'd like to see the ceiling heights for this area. What you see right up here are some fire protection piping laid out by someone. Point out that the designer of this system was not myself, but we do have 8'8" ceilings around the soffits, if you will, and up to 10-foot ceiling out in the middle of the room. Also point out that the room that I'm interested in is over 25 feet, but less than 26 feet wide. All right, so back to our 3D view, and that means that I can bring up the SprinkCAD Connect. Now, I'm going to pause for a moment and log in. As you can see, I've logged in as a user, Rob User Smith, and my manager, Rob Manager Smith, created a project named Autodesk University 2019 School. I'm going to create a new design area. So a design area represents essentially, you could say, a portion of the building, but it's basically a view into the code where you'd like to know what is the required density, what's the required square footage, what are the code paragraphs that are applicable to this particular density and building type. So area name, this is going to be the Southeast multi-purpose room. Area name, Southeast multi-purpose room. Now you'll see that I have access to a number of codes, NFPA 13 2019 being the latest available. We also cover the EN 12845 2016 edition. And in NFPA 13 we go back quite a few years. This is new, and as the years go by we'll add to our EN 12845 history. Your community may be working in an earlier version like 2010, 13, or 16, but I'm going to jump straight to the 2019. Now, based on the code, the hazard types that are present within that code will be listed. Light hazard is one of the commercial hazards. So even though we could go into rack storage, storage and display in retail, baled cotton, high bay storage, idle pallet storage, a lot of very interesting things here if you are interested in doing research for fire protection requirements in various types of commodity storage, then this is a great way to get fast information on that. Within the commercial, it's pretty simple. We have the extra and the ordinary and the light. This is a light hazard area, so I'll say save. That's populated here in the bottom half of the screen. I have a Southeast multipurpose room. And now I'm going to search the code. Searching the code, because of the choices I made in the previous screen, I see a specific set of conditions that can be answered. For instance, are there hose stations within the building structure? And the answer is no. What is the ceiling height? So as we saw in the Revit model, we have a 10-foot ceiling height. Does the ceiling or roof pitch over 2 and 12? Now, because I'm dealing with pendant sprinkler heads inside of a room, the ceiling doesn't pitch. If I were dealing with sprinkler spacing below a structure, such as a wooden roof, then is the pitch over 2 and 12? Yes or no? That's the checkbox. Do I have unsprinklered combustible concealed spaces? Are there unprotected ceiling pockets? It is new construction. Are there unprotected cloud ceiling areas? So you see, these are the questions being asked by the program based on the fact that I'm simply doing commercial light hazard commodity. If we were into rack storage or something of that nature, this list of choices would be much greater, such as palletized storage, bin box storage, solid pile or solid rack surfaces, whatnot. So I'm going to hit the search, and on the right hand side I get a series of density solutions. If I were doing standard spray sprinklers of a quick response nature, then I know that my minimum K factor is 5.6. I have to have at least 5 heads flowing, and the minimum pressure is 7 psi, density of 0.1. And minimum remote area size in square feet is 900. And you can also run this program in metric, and you'll get all of these results in metric data. I'm interested in extended coverage. Now, that's primarily because I've seen the model, and I know that the person who performed the design on that model did use extended coverage heads. Extended coverage quick response, we have 2 rows here. The difference between them, I'll pick this row, and down at the bottom we get details and references. Now, one of the details worth noting is the head orientation is sidewall. This particular row deals with sidewall sprinklers. And so I'm going to choose the other row that is extended coverage quick response. And now I see my head orientation is upright or pendant. So at a 0.10 density, the original required square footage for a light hazard area is 1,500 square feet, but there's an area adjustment given to us of 40% reduction, and that's where we come up with the 900 square feet that you see up in the top table. The bottom half of this screen has code references. Now, there's a portion of this particular screen that's slid off the bottom of my recording area. I think you can see it all, but essentially this walks you through paragraph by paragraph the code references, again, from the 2019 code. Because of my choice, you may be looking at a different code, in which case these paragraph references would refer to the code book you're dealing with. And this walks you through tables, paragraphs, and there are essentially paraphrased references to what that paragraph reads. Of course, you need to read those paragraphs yourself and validate the information yourself. Okay. I can also click Show Report, in which case I get this PDF view of exactly the same information. So my project name and address, the conditions that I set, the selection data that I chose. This is essentially referencing the row of data on that top right area of the screen. I said I wanted to use this particular result with extended coverage quick response heads. And this gives me the data behind that. Maximum area size 52,000 square feet, a supply duration of 30 minutes with a hose demand requirement of 100 GPM. And then we have the references, 2 pages, or the bottom of the first page and then the second page, all of those references. So I can print this using the standard Adobe mechanisms. I can save it to disk, etc. And that way I can turn in the report with my submittals to the authority having jurisdiction. Okay, back to Revit. Armed with that information, I'm now going to proceed with doing some sprinkler layout in this southeast corner of the building. First thing I want to do, and again, I'm something of a novice, is I'm going to hide the building outline so that I now have a 3D view of my fire protection system. Okay, you may notice, if you're very perceptive, a slight difference in my model because I had to make a change here. I had a plan that was not showing fire protection piping. As I said, I'm something of a novice here, and so I had to find out how to switch that over. I still don't know how to switch the sub-discipline of this particular plan from HVAC, but nonetheless we do see fire protection piping. This is the layout I want to work with. So I'm going to switch back over. No, let's stay here. All right, what did I learn? I learned that I require a 900 square foot area, and based on my understanding of the layout of this system, again looking at the 3D, here's my source over here. This is the sprinkler riser, and my supply main comes across the building, essentially feeding a great big loop. This loop is broken up into sub-loops. You could call it a grid, but I think it's more loop than grid. And it ties in across the backside here, but then there's an extension here that is nothing more than a tree. So I'm going to start in this portion of the building looking at this set of pipes that are essentially a tree system. Again, this was laid out by someone else. Pipe type standard, I'm seeing a little bit of slope in the pipe. No slope in the pipe. Pipe type standard. Pipes are at 11'8", and what I was looking for was the internal diameter 1¼ inch nominal. We also have drops to sprinkler heads. The drops are 1 inch size, and in some cases I thought I'd seen some 3/4 inch pipe, but not in this portion of the building. And the sprinklers are Viking extended coverage VK 534. So somebody's laid this system out. My goal is to do hydraulic calculations. Fire protection piping. Okay, so 900 square feet. Now, I'm very new. I'm going to say this repeatedly. I'm very new to Revit. And the advantage here is that the SprinkCAD toolbar allows me to do a whole lot of things in Revit that I would have an extremely hard time doing on my own. Okay, so I've already switched over to the Annotate tab, and I'm going to demonstrate how to use a region in order to establish the minimum size of my remote area. NFPA 13 specifies, I believe that this is the inside of the wall. NFPA 13 specifies that the minimum line length in the remote area will be 1.2 times the square root of the area. The area being 900 square feet, the square root being 30 feet. 1.2 times 30 is 36. When I stretch this line out to about halfway between these heads, I'm only at 31'6" from the corner. By the time I reach 36 feet, I'm clearly into the third head, so I'll come out and I see that halfway between the third and fourth head is about 49 feet. Not sure exactly. I'm going to say about 49 feet. I'm going to come across the room halfway between the second and the third branch line. Now, when I say branch line, I actually do mean the sprinkler heads. So I'm eyeballing this. If there are better ways to do it in Revit, I don't know them yet. I'm looking at 19'6", perhaps 20 feet. And if I do the math on that, I believe that just those 2 branch lines are going to satisfy the 900 square feet. We'll check it by finishing this space. This looks like it's about halfway across, about halfway between, if not a little bit under, and I'm looking at 955 square feet. So these 6 sprinklers satisfy the 900 square feet. And if you remember from what we saw, that 5 sprinklers was the minimum. We have 6, so we're good in that regard. So I click off and oops, everything disappears. Again, being a Revit newbie, this took me a little time to figure out. If I come to this particular object and change its view graphics. Now there's probably again a better way to accomplish this, but I'm just going to change its transparency down to about 95%. Now I can see it, but the sprinkler work is still visible underneath. Then I would add some kind of a text or tag to say this is my design area. But I'm not going to do that right now because we've got a job to do, and that is to calculate some fire sprinklers. So in order to generate an NFPA 13 style report, all I really need to do is identify a source point and identify the flowing sprinklers. But all of that information lives within the context of a design area. So I'm going to create this design area. Now here's where I'll mention that SprinkCAD is a licensed piece of software. And the SprinkCAD for Revit tools are also licensed software. So if I hadn't mentioned that before, this entire demonstration is about the licensed software SprinkCAD for Revit, and that means that this one isn't free, unlike the SprinkCode Connect software. You have to contact your SprinkCAD distributor at SprinkCAD.com, www.SprinkCAD.com, and talk to them about getting a license. I'm going to create a new design area. Default name is DA1. I can rename that to whatever I like. Location, I'll say southwest. Oops, that was southeast, wasn't it? Multi-purpose room. I can create either wet or dry sprinkler calculations. Now, a dry calculation still uses water as the system type, the difference being that a dry calculation, you must have a dry valve that separates the water from the air. In this design, what I have doesn't necessarily qualify as a dry valve at the moment. I'm going to go with a wet calculation. You can also choose between demand and supply calculations. Without going very deep into the subject, a demand calculation is one where you begin with the operating fire sprinklers. Or in the case of a standpipe calculation, you begin at the most demanding standpipe outlet where pressure and flow are specified by code. And you establish the required pressure and flow at that most remote outlet, be it sprinkler or standpipe outlet or fire hydrant in the case of calculations for fire flow in a building site. You establish the required pressure and flow, and the program will then calculate back to the source point and tell you what is the required pressure and the required flow to meet that demand at that most remote point, taking in all of the other flowing outlets and how much they flow based on their actual pressure in that minimum pressure flow condition. A supply calculation is one in which the program takes advantage of the full force of the source point, and it will tell you this is how much fluid, water, whatever will exit out of your open fire sprinklers or standpipe outlets or fire hydrants based on the pressures available, based on the pipe sizes, based on the elevations, based on, again, the number of open flowing outlets. The difference being, in one case, you find out what's the maximum I can expect to get out of all of these open outlets versus what is the minimum flow requirement and what is then required at the source point. If your goal is to perform normal NFPA 13 calculations, they are demand style calculations. The program is capable of calculating with both Hayes and Williams and Darcy-Weisbach formulas. Hayes and Williams, the more normal for the NFPA, which defaults to water at 60 degrees. And this is based on water coming out from underneath the ground in that typical situation, but there are options there. Calculation engine is set to SprinkCAD by default. We do have a secondary engine built into the software, but it is very specifically used for European calculations, in particular in Great Britain. Density, very important point. My density was specified as a 0.1, and that, of course, is in imperial units. You can also, if you're in a metric drawing, all of this data is going to be entered in metric units. But I have a 0.1 density. The code specified 100 gallons of additional outside hose. Now, you may recall that I told the program I did not have any hose stations. That's because within this drawing, within the model between my most remote sprinkler and my source point, hiding back here, there are no hose stations. If there were, within the software, we have the ability to specify hose locations. You specify an outlet, you say this outlet is a hose, it needs to flow this much water in these design area calculations, because different design areas might draw water from different hose stations. But in my case, there are no in the building or just outside the building hose outlets, and so I have what's called additional outside hose. This is hose water that's required to be included in the charge against the source's capabilities per NFPA 13. So even if there are no hoses on site, even if there are no hydrants within the envelope of the fire protection system that we're calculating, again, between the source point and the flowing sprinkler heads, if the nearest hose outlet is a hydrant beyond the scope of our building, this additional outside hose will act as a reduction to the power of the source point. And that is all according to NFPA 13 requirements. And you'll find the same basic requirements in all of the different codes that are referenced and processed according to the software. Its occupancy classification is light hazard, and I was told that I have a 900 square foot remote area minimum. And then I'll just put in a note here, demo calculation. Just in case anybody gets a hold of my calculations and tries to submit them as their own. Wouldn't want that. Okay, so I've created a design area. I click OK. I could create another one. I could create as many as I need for calculation of the building. Having created that design area, I'm also going to back up one step to the left, job information. This is a simple screen for the information that is going to show up on my cover sheet. The software does not pick up the data inherent in this Revit model. In case you do have project data within the model, we're not at the point where we're picking that information up automatically yet, but remember that this recording and this software is, the recording was made in November of 2019. If you're seeing this at a later date, we may have added that feature by then. I'm going to pause this recording and fill in this screen. Okay, so moments later we have job name elementary school with an address on Main Street in Anytown, Pennsylvania, and a contract number and a date. Contractor name, So that's my company, Rob's Demos. Designer named Rob. He's on Other Street, Other Town, Pennsylvania, USA, with a phone number of 800-555-1212. If you have any questions about this, just call 800-555-1212 and they'll tell you what time it is. Email rob@notreally.com. If you're in the class, you'll get my email address, and if you're reading this online or if you have access online, I'm sure that my contact information is there, but I'm not putting this here because this may end up on YouTube. And the authority having jurisdiction is Rob's Reviews. Okay, so we're back in Revit, and I did job information and design areas. I have created, no, I have not. I've not yet created a source. So let's have a look at that. I'm going to go to my 3D view and zoom out a little bit. I don't know how I got back out there. Zoom in. As you can see, there's two risers coming off of a manifold, and this is the point of connection, the stub end to the building. Now, one of the requirements for our source node is that the information needs to live on a fitting. Again, being recorded in November of 2019, it's possible that the software may have a slight modification in the near future that handles this. But all I have to do, if I have a pipe that has no fitting, is put a cap on the end of it, whatever type of cap it is that Revit wants to put on the end of that pipe. That's going to be fine. I'll also mention that a source node in the current version of our software, the source needs to sit on a fitting that is connected to one and only one pipe. Cannot be a T or an elbow at this location. It is possible, I suppose, that there could be a T here, but only one pipe can be coming out of that T. So in this drop down, I have a number of things that I can add to the system. I'm interested in adding a supply reference point. I'll mention while I'm here, the very first item is add a sprinkler reference. We'll be doing those in a moment. Next item down is a hose reference. I talked about that. The fact that I can place a hose node, and that hose will flow additional water within a hydraulic calculation. I'm about to do a supply. Below that is the SDN, or standpipe demand node. A standpipe demand node is used when you have a standpipe outlet that needs a specific flow at a specific pressure. So highest hose outlet on a standpipe, for instance. Then all of the other flowing reference points are simply hose nodes. And the difference is only one node can drive the pressure requirement for a calculation. The others simply add water to that flow rate at the pressure at that location. And we don't specify hose pressure at every hose. We specify it at the one most remote. And that's true for fire hydrants as well. Node references and orifice plates, not going to talk about those, but the program does these automatically. Node references and orifice plates are specifically used for throttling fire protection flow in those jurisdictions that allow them. Generally speaking, not the case in NFPA, any jurisdiction operating under National Fire Protection Association codes. Okay, add supply ref. Up comes dialog. Dialog gives me a prefix. We default to SRC. You can change that to however you want. SRC number 1 being the first source node that I've entered, and a date of a flow test. So let's just assume that I got this yesterday. And the location would be the point of connection. Could be more specific, things like location relative to some high fire hydrant number, relative to a column line grid number on a project, or street address. And the source of the flow test, well, Where else would I get this but Rob's Water Flow Company? Okay, you can make tank adjustments either by pressure or by elevation in the case where you're performing calculations related to a tank. You can also specify a pump as a supply point, and we have a large list of fire protection pumps that are included here. My experience in the industry has been that no two pumps are alike, and so I generally just go in and fill out the data here based on the actual pump curve if I'm calculating to a pump. This would be like if there was a vertical turbine pump here drafting water from a tank, then the source point becomes basically the pump data. I'm going to clear out this data that came in from this pump, and I'm going to go with the more typical in the United States is that I've got a water main out in the street, and I've got water flow information from a fire department, water purveyor, and they've told me that I have 120 psi static. That's the pressure at a zero flow. I add that data point. Supply curve requires at minimum 2 data points. Second data point, let's say that I have 80 psi residual flowing 750 GPM. I add that data point. So here's a very simple curve, 120 pounds static, 80 pounds at a 750 GPM flow. There's also a space for an additional pump curve. This is the unique condition where you have data at a given point, but somewhere out beyond, again, in the same way that you might have hydrants down the street that impact the hose flow, the outside hose requirement, you might have a pump operating elsewhere that is changing the results of your data at this location. But generally, if you have a known point with known data points, the easiest thing is just to enter those here on the left. All right, I'll say OK. I'm going to pick that cap right there, and I get a little label here that says source 1. If I had additional sources, I could go and click on those, and I generate source 2, source 3, etc. Okay. I'll come over here. I'm going to work in this 3D view just because it'll make it easy to grab a hold of individual sprinklers and not accidentally pick up on drop nipples or other pipes. And I'll go to the Add Sprinkler Reference Nodes. Sprinkler Reference Node, because I only have one design area, it comes up pre-selected that I must be flowing water in Design Area 1 because it's the only design area in the list. These are overhead sprinklers, overhead as opposed to in racks. And my prefix is going to be S with a starting number of 1. And now I have a place for a sprinkler coverage in square feet. So I'd looked at this layout previously, and these heads were laid out using about 18 by 18 spacing in this particular area. The heads are no more than 18 feet apart in either direction. And so this particular model of sprinkler head that is used is a sprinkler head that operates at 324 square feet based on 18 by 18 with a minimum GPM flow of 33. So I'm going to enter that 324 here as a coverage. You know that the density was set to 0.1, and density times coverage is going to establish the minimum flow rate for these sprinkler heads, so that would be 32.4 gallons. However, the cut sheet for this particular sprinkler head does require 33 GPM. So I could have put 330 here, but I also note that the minimum pressure, according to the manufacturer, is 8.7 psi. on the 11.2 K-factor head. So I'll just put in the minimum pressure. The program will balance these two and it'll say which is the more demanding condition. The sprinkler coverage times the density, 32.4 GPM, or the minimum pressure of 8.7 psi. Square root times the K factor, 11.2, is going to deliver the 33 GPM requirement according to the manufacturer's cut sheet. Whichever way you calculate that, whichever value you put in that requires the higher actual flow, that's the actual flow that you're going to get as a minimum out of these sprinkler heads. Okay. Density override, I don't need to specify because the design area already has a density associated to it. It's a 0.1 density. The density override is used for very specific sprinkler heads that must operate at a higher density for some reason, such as they're part of another building area that has a greater requirement, but I had to include that sprinkler head due to my physical space footprint, things of that nature. But that's not the case here, so no density override required. I click OK, and I touch a sprinkler, and you see that it has identified that as S1 in design area 1. And then here's S2. I move over a bit, S3, and watch out for that cube, 4, 5, and 6. And that's it. So right mouse click cancel, or I could hit the escape key. And I haven't saved my project for a while. Okay, fine. Save my project. Thank you, Mr. Revit. So I've identified the flowing heads. I've identified a source point. And the next step is relatively straightforward. I ask the program to run SprinkCAD. SprinkCAD output and send to SprinkCAD are two other commands that could come into play at the time, but let me just identify. Running the SprinkCAD means I'm going to ask the software to run this hydraulic calculation. Sending to SprinkCAD is a special condition used when you have a system where things are not quite connected correctly. Pipes are not 100% connected to other pipes. The SprinkCAD program requires under the Run SprinkCAD that we send a complete system in for calculations. If, on the other hand, you have broken systems, send to SprinkCAD allows you to grab multiple sections of piping, send them into the calculation software in their broken condition. You fix those breakage points, and then you can run those calculations. But in our case, I'm trusting that this system is all one piece. So the program asks me to select a pipe. So it's going to use this. I'll pick a pipe in the design area, but it's not necessary. I could pick a pipe over here and out in the looped area or near the riser. It really doesn't matter. I select a pipe, and you see, if you can tell by the recording, the color of all of these pipes has changed to blue. And I'm told that there were 1,436 elements selected. Does it look to me like I've got everything I need? And I'm going to say yes. So there are some pipes over here that are not selected. They're still black. Well, that's because they were not connected to the primary system, but they seem to be a portion of a design that was underway for another area. It's not part of what I need to calculate. So I say yes, proceed. The next step is mapping. Now, this is the mapping dialog. Make it a little bit bigger. And what this shows me are pipes, sprinklers, valves, and if there was a pump, there'd be a section for pumps. This is what was found within this model. In order to run the calculations, the SprinkCAD software, SprinkCalc, is the particular component involved. The SprinkCalc software requires very specific, very accurate information about the pipes, the heads, the valves. We cannot rely on the data coming straight across from the Revit model. And so each element important to the hydraulics needs to be identified to an element in your database. So again, having purchased the software and installed the software, it comes with a basic database of parts. The one that I'm about to run is the default database. So I can look at this line and I see that the pipe types used in Revit were all standard. The quantity of each type is shown here. The material, it's all copper pipe. Nominal diameters, 4-inch, 2-inch, 1-inch, 3-inch, 2.5, etc. The outside diameter and the inside diameter, in case this information is very helpful. If I don't recognize some of the other parts, I might use this data to identify exactly what was the intent of the designer that laid out this system. Or maybe I'm really not interested in his intent. Maybe I'm interested in calculating this based on the way that our company is going to install the system. So roughness and relative roughness is data that comes in from Revit based on what's in there, but it's not necessarily reliable. And the fact that things are red is just telling me that what has been mapped and what has not been mapped. So I'm going to start with 4-inch nominal diameter. And I could choose, this is the view of the Sprink base selection screen. We have pipe codes, size labels, and there are even subtypes and end preps and lengths of pipe. But what really matters here is what kind of pipe. Do I want Schedule 10, or are we interested in the copper that was drawn? So if I'm going to stick with copper, I would use this copper pipe code and then select the diameter and select the record. But in my case, I'm going to assume that the designer who did this, he just used standard pipe because he was just doing a quick layout. Maybe he did set the sizes with some intent, but I'm going to specify Schedule 10 black pipe. And that was 4-inch nominal diameter, so I'm going to sort on the 4-inch. I don't really need to worry about these other filters. Everything over here is definitely Schedule 10 black pipe, 4-inch diameter. Some of it is domestic, some of it is import, domestic and import. If that matters, if I hover over, I'll see additional information about the record. For instance, is it a 24-footer? Is it a 21-footer? Things of that nature. It might be 21-footers or 24-footers. All that really matters is that I'm going to highlight it and pick OK down here. And now it's been mapped. So you see that everything switches to black. And next item in the list, I'll just go top to bottom. 2-inch. Let's say that 2-inch and below, 2-inch through 1-inch, I'm going to use Schedule 40. So I select Steel Schedule 40, 2-inch, and I'll pick one of these records. I can double click as well as use the OK button. 1-inch nominal diameter, so again I'm going to go with Schedule 40 black, 1-inch pipe, and pick a record. 3-inch, so we're back into the Schedule 10 range, light wall pipe. Schedule 10, 3-inch, pick a record. 2.5-inch. Schedule 10 black, 2.5, select the record. 1.25 inch, so we're going back to Schedule 40. 1.25 inch, record. And 3/4 inch. Now, in steel pipe, it's not normal to use 3/4 inch pipe. In copper and plastic, that's acceptable, but I'm going to map this 3/4 inch copper also as steel Schedule 40 1-inch pipe. So even though the designer set it as 3/4, I'm mapping it to 1 inch. And then finally, we have some 6-inch copper. Go out and buy that, and you'll find out that copper's rather expensive. Schedule 10 black. 6-inch pipe isn't exactly cheap either, I'll say that, but glad I don't have any of that in my house. Okay, so I've mapped all the pipe. Now we go on to sprinklers. Now, mapping sprinklers, I want to be a little more careful about this because there are a lot of different types of sprinklers. I can see from the names used, these were Viking heads that were used in this design, VK534, so I can look that up online and I'll learn information about that. It happens to be an extended coverage, quick response sprinkler. The 534 can be laid out either at 18 by 18 for light hazard quick response, or in the case of one of the uses within this particular design, even though it could have been a 14 by 14 head, in order to use it in light hazard quick response, I have to treat it as a 16 by 16 head at 256 square feet. But that's a minor sub point here. Okay, so I'm going to map. Now, I actually may have Viking sprinkler heads in my database. It's entirely possible, but I'm instead going to use my preferred. So I'll go to extended coverage because I know this is an extended coverage head. I know that it is a pendant head, and I know that the K factor was 11.2. So by sorting on those three, I can see that there are both 3/4 inch and 1 inch thread size heads that come into play with that 11.2. If I specify the 1 inch heads, I only want to see the 1 inch because this maybe there's a reason why. Then I can see that I have the DS2 models. Pretty much all of these 1 inch heads are DS2. Okay, so I'm going to click out of the DS2, click on the 3/4, and now here's the sprinkler heads I was looking for, the EC11 pendant. Over on the right, I can see the finish. So I've got some white heads, some lead coated, some chrome heads. Not that the finish matters, but in this case they were white heads, and so the difference are temperatures, 135, 155, 175, and 200. This was a 155 degree head, and so I'm selecting that head, and here we have the 11.2K 3/4 inch NPT EC11 pendant. There are 35 VK630 heads in the design. These are sidewall heads. Now there aren't any sidewalls in my design area, but because they're part of the Revit model, I need to map those. Here we'll map the VK630, which is an extended coverage sidewall head with an 8.0 K factor, and white 155 degrees, double click, and in that comes. Finally, these 12 VK600s. Now these, I found these are on the model. These are 5.6 K factor pendant heads. They're also extended coverage, I believe, and so just in case I'm taking extended coverage. Again, they're not in my actual design area. 5.6 K factor, and I have these 1/2 inch. I'll use the EC5 quick response 155. Finally, we come to valves. So what I do see is that it is there are two of them. There's a 4-inch double interlock pre-action valve from someone else. It's not a Tyco valve. So first thing I'll do is find a pre-action system valve in the 4-inch size, and I see that these come in both flanged and grooved. So I'll pick, just to isolate that a little bit, I'll pick grooved, and in a 4-inch groove by groove pre-action valve we have the DV5A and the DV5 type A pre-action. Not really any difference in these pre-action valves. There are differences in the trims and whatnot. In order to actually investigate the real difference, I'd have to go in looking at the part numbers. So I'm just going to pick the first one. And as you can see now, everything has been mapped, and I can proceed. If I need to run another calculation, if I need to make modifications to this system and run the calculation again, even if I close the model and return to it another day, all of this mapping information is saved within the model, so I don't have to go through that again. So when I click proceed, the calculation software begins, and up comes my hydraulic results. In this screen there's a number of things that we can learn before we dig any deeper, and I'll try to do some zooming in this recording in order to highlight the different areas. Across the top of the screen we see that we calculated design area number 1, light hazard occupancy at 900 square feet, and the total water flowing at the source is 315.705. Now this 0.705, there are adjustments within the software to specify how many decimal places you want to see. When you're dealing with liters, you don't want to see 0.705 liters. Clearly, you can round off to the single digit on liters. With NFPA 13 and the Imperial, it's pretty standard to round off to 1 decimal place as opposed to 3. And same thing in pressure. You can round off to a single decimal point here, so that might show up as 79.7. Minimum density is 0.102. Why is that? Because at the very minimum, and I'll move down to the left here, the very minimum, we have a discharge rate of 33 and just a little bit more than 33 gallons, but rounded off to 1 decimal place, that would show up as 33.0, and that's based on the minimum pressure as specified by the manufacturer. Which sprinkler head is flowing? That's at node number S1, the end of the first branch line in this case. Maximum coverage, minimum coverage, and pressure at the source is specified here on the left-hand side. So we have a required flow of 79.66. So looking at the graph, that line and those 2 dots are just a hair underneath 80, 79.66. And what is available at that flow rate? 111.9 available. And you can see that point highlighted here on the blue supply curve. Flow at the source, 315.705 gallons. Again, that's what's required. That's what's available at that flow rate. Moving back up to the top, we see some of the same information. This also tells us that 6 sprinklers are flowing and that there's a additional hose stream, a total hose stream of 100 gallons. Okay, moving down, there are a number of types of different data points that could be generated onto the screen, such as adjustments for safety pressure, which I'd have to fill in, required safety pressure in pounds or percent. I'm not going to delve deeply into that at this point in time. It's even possible to play with adjustments to hose flow. You can apply the hose flow to the demand curve, as is done here, points D2 to D3, and some people prefer to see the flow rate generated as an adjustment to the supply curve. But in order to see that, I have to turn on the supply adjusted for additional outside hose, and you see this new red line that shows the reduction to the flow curve. And now we don't see the hose as an extension of the design curve, rather we see it as a reduction to the supply curve. It's 6 of one, half dozen of the other, because in either case, the required pressure at the source, the available pressure at the source, at the required flow rate did not change. So I'll switch that back. Show that in that way. Okay. Next thing to point out about the results. Let's try and make this a little bit bigger. Normally I would use full screen, but because of this particular recording, I'm not actually recording the entire contents of my screen, so I have to adjust things manually. The diagram can be seen here, and the diagram can be viewed from various angles. This is the way I had it set up in the Revit model, so this makes the most sense to me. And this diagram can be used for understanding the flow characteristics of a system. For instance, come here, I did a right mouse click on pipe labels, and I can see things like how much water is flowing through the different pipes. So zoom in a little bit and we'll see that there's 170.5 gallons flowing across the back side of what I would call this loop system. Now there's 45 gallons entering into this side of the loop. It splits into 22 and 22, comes around, splits again, 22 and 22, and then that same 45 gallons is now flowing across this way, where it splits again, goes down, joins in, splits again, comes back. That same 45 gallons comes in on this side. So basically we have a loop starting at this point, ending at this point, where on the short side 170 gallons is moving across, and on the long side, which is a couple of separate loops, we have 45 gallons total moving around that side of the loop, for a total flow of 215 gallons moving down through the riser and through the valve. 215, but you remember that the flow curve, the graph, was indicating 315. That's because the source is providing 215 gallons into the system, and an additional 100 gallons is being deducted from the source as part of the additional outside hose flow. Over in the remote area, I can see 33 gallons flowing up that drop nipple. 33 gallons continues over where it joins the flow from the second sprinkler, and now we have 66 gallons flowing through here. Third sprinkler comes in and we have 107 gallons flowing down this pipe. This pipe, due to the fact that there's a very slightly higher pressure acting upon this fitting back here, this pipe is flowing 108 for a total of 215 point whatever. Okay, so that's just one of the pieces of information that can be seen. Maybe you'd like to come in here and see what kind of friction losses you've got. So we can go into friction pressure loss. So we can see that we're losing 1.6 pounds up the drop nipple. Another little bit of loss over here on the arm over, 1.5 pounds in the first piece of pipe, 5 3/4 pounds through the second, 37-pound loss on this long piece of pipe right here. Now, normally that might cause a little bit of concern, 37.5 pounds of loss in one part of the system, but based on our hydraulic calculations, again going back to the graph, we've got a nice comfortable surplus from the 80 up to the 111 pound. You can do the math right there and see what the actual surplus is, or we could wait until we see the print output. Right, back to the diagram. What else might you want to look at? Some people prefer to look at the friction loss as a per foot of pipe. You can investigate internal diameters. You can look to see what fittings have been applied to specific pipes. You can even see the elevation pressure loss associated with a given run of pipe. You can look to see what your sizes and schedules are. So we could look here and see that, which we hadn't really investigated previously, that the entire system on these branch lines is 1.25 inch pipe, start to end. We have a 1-inch arm over and a 1-inch drop. Our cross main is 2.5 inch all the way back until it converts over to 4 at this point. As I recall from the model, this is the general area where we were feeding the second floor piping. So they ran 4-inch out to here, perhaps as a requirement for the second floor calculations. We have 4-inch. But beyond that point, 2.5, and feeding this loop is 3-inch pipe, probably over designed here on the 3-inch, and even 2-inch on all these branch lines. We won't really know whether that is required or not until we do some calculations in one of these areas along these gridded loop pieces. Okay, you can then turn that off. And there's information to be seen on the actual nodes, such as the node numbers. I want to know that's actually node reference. Device name will be things like the sprinkler head name. How much water is coming out of these? So on an individual basis, we can see what the flow rates are. We can look at the K factors of our sprinkler heads, make sure that we've got that right. We might want to look at the pressure total at any given head. So we see that the start pressure for that head is 8.7 psi, and we have as much as 13.5 pounds flowing here. There are systems where the difference in pressure from the most to the least, I should say the highest to the lowest pressure across the system can be an important point of review. Required density, required pressure, or over discharge. Some people might come to over discharge and find out, well, how much water am I flowing out of that head that I don't need? Okay, I'm going to turn those off. Now, one of the reasons for making this big and turning things off is that when you do print the hydraulic calculation, if you want to capture the system layout, especially if you're looking for flow direction arrows in gridded systems, you have to show direction. So here we have the option to show or hide the flow direction and even to set the size of those little arrows that show up. I'm not going to bother with that here. If you needed to, you can actually take a diagram capture. So perhaps you want to get very specific portions of the system, capture those images, and then include them in your calculation printout. I'll just do the basic here, zoom in like that, and I'm about to hit print preview. Before I do, I'll point out that there's also a DXF option. You can generate a DXF file that can then be imported into AutoCAD. Okay, print preview. I've got a 2-screen view here, so let's make things a little bigger. Zoom in. That'll bring it back to a single screen and make it fit. Okay. Cover sheet. So here we have the name, contract number, city, address, date, contractor information, same basic information I entered in that job. The design of the system, the fact that this is DA1, and the location, the occupancy classification. The program prints out the minimum density, area of application, coverage per head, number of heads calculated. There were no in-rack sprinklers, but we had 100 gallons of hose stream. We had total water of 315. All of this information is required by NFPA. And we have the volume of the system in gallons. Water supply information. Here's the date, location, and source. On the next page, we'll see more about the water supply and our notes. Hydraulic analysis. The mode, the model, which is the formula used, and the fact that it's a demand calculation. The water, again, 60 degrees. And here's the source curve data that we entered for this supply. If I had multiple data points, like was provided by those pumps, they would be filled in here. Hose data, the only hoses we had was additional outside hose, 100. Sprinkler flow, another reference to the NRAC flow, any other or custom defined flows, total flow. And then we have the required safety margin, which we didn't fill in, and the pressure and flow at the source. Now you'll notice that 215 is only the flow going into the system from the source point. If you were running pump calculations, there's another line there for demand without the system pump. Sometimes using a fire protection pump, you can get some odd results back at the source point. Here is our curve, results curve, and the labels for that curve, the D1, D2, D3 point, the S1, S2 point. Those are laid out down here. And we have the intersections and safety margins. Now, intersections are primarily used by insurance companies. It looks at the maximum amount of water that might be extracted from the system. Now we have the open heads table. This is very, very helpful information. It shows the flowing sprinkler heads, their type, their coverage in square feet, and their K factor. These next three columns tell us what was the required density and flow and pressure at those heads. The pressure required of 8.7 is calculated back through the coverage of the head, and it yields a minimum density of 0.102. Minimum flow, also based upon minimum pressure, 33.035. But here we have the calculated values for these heads. So this table very quickly will drive you to understand which sprinkler head is driving the calculation. If you didn't have any other way of knowing, you could see here that S1 is the sprinkler that's operating at its minimum requirements. The others are over discharging to some extent. Move down through this node data table. This layout, this header, is essentially established by NFPA 13 in terms of minimum amount of information that must be displayed about the heads, their elevation. This is something that we have added, the age group, but the elevation, the total pressure, discharge from open heads, the K factor of open heads, the required discharge and required pressure. Then we get to the pipe data. I'm going to spend just a moment in this area talking about path style calculations. So we have a header across the top that tells us that this first block of data, this first long rectangle, this takes us from node 1 to node 2. So any hydraulic calculation program is going to give you on a essentially, I don't want to say a pipe by pipe basis, but within a run of pipe that has the same internal diameter, the same schedule of pipe, the same flow rate, then these hydraulic calculation programs will represent to you what's the pressure at the starting point, what's the pressure at the ending point, and what are the parameters of that run of piping. In our case, we're going from sprinkler number 1, which is 1-inch pipe, for a distance of 4 feet length and a fitting length of 4 feet, which is our two 90-degree elbows, two US 90s, totaling 4 feet of friction loss, or 4 feet of additional length, for a total length of 8 theoretical feet of piping. Now this is standard NFPA 13 approach to hydraulic calculations. That water was carried from S1 to node N477. Now, we didn't place that node, but we will see it. The elevations of these nodes are specified. S1 is 8'8", and this other node is at 11'8". The K factor for S1 is 11.2. We added 33 gallons at that S1, and we carried that 33 gallons through this pipe. What pipe? a piece of 1 inch with an internal diameter of 1.049. Again, there are 2 elbows, the one at the top of the drop nipple and one where the arm over connects to the branch line. 4 feet plus the fitting. The C factor is 120. The pressure loss per foot is 0.328. And the total pressure of 8.7, we have a pressure gain in the drop nipple, 1.3 psi of elevation gain. But we also had a loss of 2.65 pounds in friction loss through that drop nipple and arm over. So as a result, we reach 10.05 pounds at node N477. So that 10.5 is the result of doing the math on these 3 numbers. 8.7 plus 2.65 is 11.35, minus 1.3 is 10.05. So now we're traveling along at the elevation of 11'8" pretty consistently through here, going from node to node. There was no water added at N477, so we carried that same 33 gallons of water through this first piece of 1¼ inch pipe, which has an internal diameter of 1.38. We see here the length of the pipe is just under 18 feet. We see the friction loss factor is lower now because we're carrying the same amount of water through a smaller piece of pipe. So friction loss factor is lower, 0.0864 versus 0.3284. And we add 1.55 pounds of friction loss to that first piece through that first piece of 1¼ inch pipe. Now we reach the second sprinkler head. And what we see here is N487. This is where we add 33 pounds, This is where we add 33.83 gallons for that second sprinkler head. It's being added at node 487 because that is the place where the 1¼ inch pipe from the first head meets the 1¼ inch pipe that will take us to the third head. And so we're going to stop right here at N487 where we're adding 33 gallons of water. And we're adding it at a pressure of 11.6 pounds. So let's take a look a little lower in the calculation at path number 2. Path number 3, there it is. Path number 3 carries us from sprinkler number 2 to node 487. It begins at 8'8", it goes up to 11'8". Of course, that's an 11.2 K factor head, and it's flowing 33.83 gallons. So that water is carried up through the rise, the drop nipple, and up to the T. Now there's a T at the top instead of 2 elbows. There's 1 elbow for 2 feet, and there's the T where the arm over meets that branch line. That's worth 5 feet. So we have a total of 7 feet of fittings along with the 4 foot of pipe to get from the branch line down to the sprinkler head for 11 feet at the 0.3432 friction loss per foot, gives us a 3.78 loss. We began this sprinkler head operating at 9.12 pounds of pressure. There was again an elevation change, and so we have an elevation gain and a friction loss. And the total when we reach the branch line is 11.6 psi. Now remember, this head is operating at a slightly higher start pressure. Why? Because the pressure needs to balance when we reach the branch line at node 487. So 11.6 pounds at node 487, 33.83 gallons. I'll go back up to the path number 1 at node 487, where the 33.83 gallons came in at a pressure of 11.6 pounds. So the pressure is in balance, the flow is in balance. Every piece of pipe is represented within a pathing report, but in a pathing style report, as opposed to some other types of printout, you can carry the water from the most remote head, S1, straight to the source in a straight line. It's basically the way it's done in hand calcs. It has been done this way in the NFPA 13 codes since before I started in the industry. It's been done in hand calcs this way forever. And if you understand how it reads, the nice thing about a pathing report is all the important information is here in path 1. You really only need to study these pipes to understand the entire sprinkler system. All the rest of the data, path 2, 3, 4, etc., this is just balancing steps. As long as the pressures are guaranteed to meet in balance at every junction point, which they are because the computer is doing the work, then your calculation is very easy to read in path number 1. You see here that there's the valve. This is where the valve is losing 0.98 pounds, and we'll see the valve curve later. So this water is carried down the 1.25" branch line. Then we transition to the 2.5" main. We pick up water from the second branch line here. An additional 108 gallons was added to the first 107 from branch line 1. This is the water from branch line 2. The 215 gallons then is carried over to the point where the loop splits off, and we looked at that. 45 gallons comes out for the loop. We continue to follow the 170 gallons through the 2.5, which then transitions to 4-inch, heads on over, through the riser, through the valve, and then finally hits some 6-inch pipe, as we saw, and makes it to the source at a required pressure of 79.66. So that's as far as I'll belabor the calculation, other than sliding down past all the pathing data and showing you the end of the calculation where we have maximum velocity, and it tells you which pipe, node numbers, maximum velocity is occurring in. And then we have the source curve, and we have the valve curve. So as many valves as you have in the calculation, they'll be included at the bottom of the calculation printout if you ask for them. And here's where we can see the actual pressure loss based on this valve's curve at the flow rate moving through that valve. We lost 0.98 psi, or 1 pound of loss. There's the hydraulic calculation printout. That essentially finishes the portion of the calculation, running a calculation in SprinkCalc and getting a printout of it. However, but wait, there's more. After the calculation is done, we return to the Revit environment and we get this data. For every design area that is calculated, and you can calculate more than one design area at a time. For every design area that's calculated, you're going to get this result back in your screen, and this can be brought up at any time after. Base of riser flow, there's a very specific way to identify a point which we're going to call the base of riser. In this calculation, it's the source point. How many heads, what's the maximum velocity, how many in-rack, how much water was moving through the in-rack system, overhead system. Again, more data about flows, system flow, additional flow, that was the additional outside hose, total flow. The required pressure, the available pressure, the surplus pressure is calculated for you right there, 32.27 psi surplus. And then specific nodes relative to design area DA1. So these nodes, you don't have to look at them, but if you want to see them, there they are. And we have all these reference nodes and some sprinkler nodes. So I'm going to take a look. Let's say that I want to see the data. Where was S1? Oh, I know where S1 was, but I thought that there was something funny going on at, pick one, N473. All right, so I double click, and there it is. It highlights it for me in the model. I can zoom in even closer if I want to by clicking on the zoom. It'll take me to a plan view and show me exactly where that particular node is in my model. All right, close that. Now, you've got something to print. in terms of the hydraulic calculations. But what about our plan view? What about this layout? In the SprinkCAD toolbar, we have Place Hydraulic Reference Tags. Place Hydraulic Reference Tags. The settings for this particular item are basically the offset in X and Y and the orientation, and whether I want to remove the existing text notes. Now, do you remember when I put these flowing nodes on the drawing, I was in the 3D view. So the remove existing hide ref text notes, those were those notes that showed up that said S1 DA1, S2 DA2, DA1. Those I wouldn't print and I wouldn't leave them visible. So I'll say yes, I want to remove those. Click OK. And what I get now, based on the settings that I used, are these hydraulic reference nodes in my plan view. So node 477 is up here where the 1 inch met the branch line. Note 487, we took a look at how the water went from S1 to 477, then came across to 487 where the water from S2 was joined in, etc. So those additional nodes, there's the 473 we took a closer look at before, and 456. Why do these matter? Because on the printout, the water is going to come to node N456, and it's going to say, well, this is the point at which the additional 108 gallons joined the calculation flow on path number 1. So you want to be able to find that in the printout of the model. And then all the places where water had to go around and split around this loop. Here's node 364 where the 45 gallons first split off to go off on the rest of this loop out here. At every junction point necessary, the program will give you this kind of data. The only time that data doesn't appear is if there's no hydraulic requirement according to NFPA 13 to represent that data on the plan. Any place where NFPA 13 specifies that a node needs to appear, you'll get them. Okay, now I'm going to take a look at my riser. By double-clicking here, we go to section number 6, and if I plan to print this out as part of my printouts for hydraulic approvals, I'll come to the SprinkCAD, say I want to place hydraulic reference tags. Again, same basic information. There's nothing here to remove, but I'll click remove anyway, just out of good habit, and there's N549. Now, the actual point it would reference is this T. This is where the water came down through the valve, transitioned from 4-inch pipe to 6-inch pipe, N549. And in the SprinkCAD software, perhaps you want to do some printing from one of your three-dimensional views. All right, so we set up the view angle however we're going to want it, and I'll go again to the toolbar and specify I want to place hydraulic tags. However, the program tells me, this 3D view must be locked before you can add tags. Okay, so being the amazing Revit user that I've become, I go and save the orientation and lock the view. And I'll give it a name. I'll call it 3DFP. Lock that view and place hydraulic tags. I'm going to remove that information in case it is there. I'd have to zoom in close to see if it's there. I think it's already been removed. I hit OK. And there's the data I was looking for. So S1 up to 477, S4 up to 460. And all of that same information, and maybe you don't like where that's located, so go ahead and move it. Remember that I had control over the X and Y offset of these values, but unfortunately I don't have individual control, and I don't want to do that. So I've learned If you drag something that you didn't intend to drag, just do an undo. Let's cancel that in this case because it didn't like that. All right, I want that piece right there to move. I want that piece right there to move. All right, so you get the idea. Now I've got something I can plot and submit to my authority having jurisdiction.